Let's do some practice on substrings of a ring. Okay, let's say we have to figure out whether the set of matrices of the form A, B, C, 0 is a subring of a ring of 2 by 2 matrices. Let's say given 2 by 2 matrices as a ring. Okay, now we know to figure out whether something is a subring or not, we need to just check for two conditions. So let A is equal to A1, B1, C1 and 0, and B is equal to A2, B2, C2, 0. Okay, now this belongs to S and this belongs to S, where S is the set of matrices of the form A, B, C and 0. Okay. Now the only thing we have to do is we have to check whether it is closed under subtraction. Whether if we subtract A and B, then do we get a matrix of the same form? So let's see. A1, B1, C1, 0 minus A2, B2, C2, 0. Now this would be A1 minus A2, B1 minus B2, C1 minus C2 and 0 minus 0, 0. Okay. So it is of the form that is required. So which means this belongs to S. Now similarly, the product A times B, A1, B1, C1, 0 times A2, B2, C2, 0, and let's multiply this. We get A1 times A2 plus 0. So A1, A2. Now the second would be A1 times B2 plus B1 times C2. This would be in the second row, we will have 0 plus 0, that is 0. 0 plus C1, C2. So again, it is of the form that is required, so it belongs to S. So since these two conditions are satisfied, therefore S is a subring of the ring of 2 by 2 matrices. Okay, so that is the first one. Now let's look at the next one. Now the set is going to be an infinite set minus 3k, minus 2k, minus k, 0k, 2k, 3k, and so on, where k is any fixed number, more precisely integer, is the subring of the ring of integers. Okay, so let R be equal to Z with addition and multiplication. S is equal to the given 0 plus or minus k plus or minus 2k plus or minus 3k and so on. Now we know this is going to be a subset of R, and here k belongs to the set of integer. Okay, now let's see whether it forms a subring. So let A is equal to m times k and B is equal to n times k, where m and n belong to the set of integers and A and B naturally will belong to the subset. Okay, so again, to prove that it forms a subring, we check A minus B is equal to m times k minus n times k, m minus n times k. Now remember, m and n are integers which is closed under addition. Subtraction is just different way of doing addition. So which means this belongs to S. since m minus n belongs to the set of integers. Okay, now let's look at the product. A times b would be mk times nk, which can be written as mn k square. But this can be written as mnk times k, right? And here mnk belongs to the set of integers. So therefore, this belongs to S. So therefore, since A minus B belongs to S and A times B belongs to S, implies that S is a subring of R. Okay, so that is the second problem. Now let's look at the third one. Now here, what we have to do is uh, prove that the subrings of the ring of integer modulo n, right? Integer modulo n under modulo addition and multiplication is in the form of mzn. So here mzn is equal to the set ma, where a belongs to zn and m belongs to z. So let's see. Uh, let A be equal to M A1, B is equal to M A2. Now here A1 and A2 belong to Zn, integer modulo n. Okay, and M belongs to Z. So remember the conditions: A minus B, M times A1 minus M times A2, which can be written as m times a1 minus a2, and this can be written as m times a3, where a3 is equal to a1 minus a2, and since a3 belongs to zn, we can say that a minus b belongs to mzn. Okay, now let's look at the product. A times B is equal to M times A1 times M times A2, which can be written as M times, because we want it in that form. So we can say A1 times M times A2. Now here, this again belongs to MZN, since A1, M and A2, the product, belongs to Zn, because this belongs to integers, this belongs to integers, and this belongs to integers. So, which basically means that MZN forms a subring under Zn. Okay, let's look at an example just to understand it clearly. So let's say we are talking of uh, integer modulo 16. So to figure out the subrings, we have to arrive at the factors of integer factors of 16. So this can be 1, 2, 4, 8 and 16. So we just take Z16 and multiply it with each one of these one by one. So this would be equal to the set 0, 1, 2, 3, that is Z16 itself. Okay, 2 times Z16 is equal to, now just multiply, 2 zeros 0, 2 ones 2, 2 twos 4, 2 threes 6, 8, so on up to 14, not 3. 4 times Z16 0, 4, 8, 12, 16 not there. So we stop. Then 8.z16. 800, 818, 8216. So stop. And finally 16z16, which gives us 0. So we have these 5 subrings. Now, this is fine for z16. But if it is a larger number, say z 1000, 2000, if it is like that, it becomes difficult. So to be able to figure out how many subrings are there, what we can do is take uh, the number and figure out its prime factorization. So 16 is 2 eights, 2 fours, 2 twos, 2 ones. So we have 2 to the power of 4. And we take the exponent and we add 1 to it, which is equal to 5. So there should be 5 subrings of Z60. Okay. Now what about 20? So 20, 2 tens, 2 fives, 5 ones. So 2 square times 5. So 2 squares times 5 to the power of 1. And here what we do is we take the exponents, add 1 to each of these and take the product. So this will give us 3 times 2, which is 6. So there will be 6 subrings of Z20. Now let's take a larger number. So this can be written as 10 cube, which can be written as 2 times 5 to the power of 3, which can be split up saying 2 cube times 5 cube. So which means now we can add 1 to each of the exponents and take the product, which will give us 4 times 4, which is 16. So which means there will be 16 subrings of Z1000. So that is subrings of a ring. That's it for now. Bye.